to talk to you about the principles of phase change materials and SunAmp. This is a CIBSE approved CPD, so I will issue certificates. What we'll do is we'll have a quick look at our responsibilities. So it stands to reason, as we're using more and more energy in the home for heating and hot water, there's a large proportion of that is used in heating and hot water. And we also need to consider business, industry and commercial sectors. So central to the question is, how can we generate domestic hot water and heating with a net zero carbon impact or a low zero carbon input? So domestic hot water is a contributing factor to carbon emissions. It's quite energy intensive. So we're getting better at improving the fabric of buildings and introducing renewables, and we're continuing to reduce energy consumption for space heating. But hot water is still a bit of a problem child. We're looking at 4,200 joules of energy to raise 1 litre of water 1 degree. So it is quite an issue. So what we're going to cover is we're going to look at the history of phase change materials. We're going to look at phase change materials, or PCM. How does it work? We'll have a look at sensible heat and latent heat, so the differences between those two. And specifically, we'll look at SunAmp and the technologies surrounding the PCM we have in our product range, and its melting point, which is 58 degrees C or above. What if we can generate domestic hot water a completely different way on the road we're all on? We'll have a little overview of SunAmp, and then we'll look at some real life examples.
Recording in progress.
Sorry, what was that? Okay. So, history of phase change materials. Everybody thinks it's something new, but it's not. 260 years ago, Joseph Black, who's a British chemist and physicist, he was best known for his fixed air experimentations of carbon dioxide, and he discovered the concept of latent heat. He also discovered bicarbonate of soda, which probably everybody is familiar with. So what he actually did within his experiments is he applied heat to ice. So if you've got a glass, you fill it full of ice, and you put a temperature to that, then what he looked at was the increase in the amount of water of the mixture. So the temperature didn't actually rise. Basically, we just the amount of water increased. So we'll look a little bit further within the presentation of latent heat. But from his early observations, he concluded that heat applied, it must have combined with the ice particles and boiling water, and it became latent, or hidden energy, hidden heat. So moving on a little bit further, 150 years later, Maria Telkis, inventor and researcher, she coined the nickname the Sun Queen, and she come up with some really good thermal devices and practical thermal devices. And she was a prolific inventor, and one of her early devices was called a solar still. So during World War II, if there was lifeboats or downed air crew, there was this little condenser. You'd collect the salt water, and then basically it would condense and make it into potable water. So this kit, it saved the lives of airmen and sailors. So she was involved in the world's first passive house in 1948. So we'll have a little look at that in the next slide. So moving on from Maria Telkis's experiments, 70 years later, the University of Edinburgh, the School of Chemistry there, they are our research and development partners. and the university was instrumental in the development of phase change materials, PCM 58. So, as I mentioned before, Maria Telkis, she began her work with solar energy as part of the conversion project at MIT. And she took an all-female team and designed the world's first solar heated home in 1948, using globosols, which is a phase change material, sodium sulfate. So this little schematic, what you're looking at is basically these box collectors, which is a solar thermal collectors. So obviously the sunlight's going to warm the box collectors, and then at the back of the box collector there's a black sheet of metal. So that heat was then piped down into the barrels of globosol, and it transferred the heat into the phase change material, and it liquefied and stored that heat. So if the temperature dropped within the building, then you would have fans. There's 12 fans all in total, and basically just like a warm air system, it would just pipe and blow the air around and warm the building. So when we think about that, going back to 1948, it was quite cutting edge, and you know, lots of cutting edge technology, and it worked quite well. But unfortunately, what they found out was they were using more power and electricity and energy to turn the fans. So eventually the project had to move across to like a traditional system. So what are phase change materials and how does it work? So in a nutshell, it's a substance that releases and absorbs enough energy to generate useful heat or cooling, because there's a vast range of phase change materials. So it can go from a minus temperature range to a very high temperature range. So in most cases, the transitional between two main states of matter. So you've got solid and then you've got liquid. And there's two principal types. You've got organic and you've got inorganic. So inorganic PCMs are salt hydrates, nitrates. They really have a good high heat of fusion. So these materials have got good latent heat values. They're non-flammable, they're non-toxic, and they're readily available and at low cost. So within the Sunamp products, we use an inorganic PCM, which is sodium acetate. And I'll explain a little bit about what sodium acetate is later in the presentation. So we've also got organic PCMs, paraffins, polyethylene glycol, so the stuff you would put around solar thermal systems. And then you've got eutectic, which is a mixture of both. So just to explain sensible heat and latent heat. So what is sensible heat? And forgive me if I'm you know, telling you all how to suck eggs, but you probably all know what sensible heat is. So it's just heat you can feel or sense. So if you put your hand on a radiator and it was hot, that's sensible heat. Equally, if you take your hand away from that, you can feel the temperature drop. That's sensible heat. Sunny day today, thermometer, you can see that temperature rising within the thermometer. So that is sensible heat. And there's a little schematic there, which shows a different temperature range, rising up to 100 degrees C, which is boiling temperature. So you can understand what sensible heat is. So what is latent heat? So when we talk about latent heat or hidden heat, we're referring to a change of state of elements. So going back to school, when we were in our science classes, solids become liquids, liquids can become gases, ice can become water, and water can evaporate into vapor. So essentially all pure substances in nature can change their state. The energy that causes these changes is called latent heat, hidden heat. Going back to Joseph Black's earlier experiments, when he applied sensible heat to his glass of ice, the glass then began to melt, but the temperature didn't go up. So once it gets to 100 degrees, then it'll change phase. It'll change into a vapor. So where is all that energy going? So again, this is a really good schematic that just shows simply we've got sensible heat, we've got our water there, hitting a temperature, and then that latent heat changing phase into the water vapor. Now, if you had a thermometer in there, it wouldn't go above 100 degrees C. You won't see an increase in the temperature, and that's because the latent heat, the hidden energy in the molecules of the water is mixing, and so that the latent heat is the energy required to achieve the process. So stands to reason, if we can capture that latent heat in the material, then that's going to be a brilliant way of using that material to store and release heat, or store cold and release cold. So it's the same principle as storing electrical energy in batteries. So if you've got your phone, you charge your phone, you can charge it, discharge it, talk, text, whatever you're going to do. So compared to sensible heat storage methods, i.e. typical domestic hot water cylinders, you're going to gain just under 2,000 kilowatt of hours based on an annual typical energy use, just by moving away from a traditional domestic hot water vessel. So PCMs make great thermal stores. They're compact, they can operate on a narrow temperature range, which means really, really low heat losses, 30% less than a traditional system. So what we've got here is this graphic, and the vertical graph shows watt hours per litre as a measurement, and then we've got a temperature range. Bear with us 1 second. Okay, so there's a few things going on with this slide. So if you look at the blue line, if we go back to our previous graphs and when we talked about sensible heat, that is sensible heat. So if we follow that blue line and raise the temperature, raised it to 100 degrees, then that is your sensible heat line. The red line is a phase change material. So if we introduce heat into it, once it gets above 58 degrees C, then the phase change material will start melting and absorbing the latent heat. And because we've got 4 times better energy density than water, we can store all our energy in less material. So, for example, if you've got 300 litre cylinder of water, then you're going to have to put a lot of energy in there to get that up to a higher temperature. We can achieve the same goal in less material. So we can put the same amount of energy in 100 litres of material, but without using as much energy as what you would need to in water, because it's got different specific heat capacities. Hope that makes sense. So essentially what would happen is, whatever your heat source is, whether that's an air source heat pump, a ground source heat pump, electrically charged from the grid, gas boiler, it does not care. As long as you're putting a heat source in there, an energy source, as soon as it hits that temperature, it starts capturing that hidden energy and stores it. So some of the challenges we had as a business was cycle stability, failure to release heat when we wanted it, slow releasing, flammability, toxicity, all those issues we needed to address. So this little video that you're seeing it's a hand warmer. So if we were doing this face to face, I would hand these out, and then you would sort of like get a tactile physical presentation of how the energy is released. So what you can see is it's actually freezing there, so it's going from its liquid to its solid state. So this is its exothermic, it's releasing heat. So within that hand warmer, there's a little metallic clip, which is embedded with phase change material. So when you click it, the friction releases the energy that's stored in there. And then once it's released its energy and it's cooled down, if you want to send that back to its state, you would drop that in boiling water and it would go from its solid to its liquid form, which is endothermic. Okay, so hopefully you have a better understanding of how phase change materials work. So what if we can generate domestic hot water a completely different way? So what are the challenges? So if we look at traditional domestic hot water cylinders, generally we'll have a coil in there. You'll have an immersion heater. So you'll have the boss of the immersion heater stuck out there, the side of the cylinder, and generally it would be in the water to heat that up. You've got to consider Legionella cycles, particularly in commercial buildings. And you've got to have little bits of other kit that goes with the cylinder, and that's down to the G3 building regulations. So if it's unvented, and what we mean by unvented is it's basically a sealed system, you've got to have certain safety valves, you've got to have an unvented system kit with expansion vessels, etc., etc. You must have a qualified engineer, and you must have an annual safety check. And you'll have some maintenance. The other thing to consider is you've got to have discharge pipe work. So if any of those safety zone valves or expansion vessels, or if that goes to a higher temperature, then you've got to get that high temperature failure out through a discharge pipe work. If it's a larger cylinder, or clarifier as it tends to be called in the commercial world, you'll need a destratification pump. And what I mean by destratification is in that cylinder you will have thermal layers. So at the top it's going to be hot, and at the bottom it's going to be cold. So the easiest way of explaining destratification is if you had a swimming pool and you put your foot on the top of the swimming pool, it's going to be warm at the top, it's going to be cold at the bottom. So we need to circulate that and destratify the thermal layers. So what you would do is you would get a pump, some pipe work, and then that pump would then circulate and destratify the thermal layers within that cylinder. So that's what we mean by destratification. Obviously, you've got on costs there, and pump costs and additional maintenance costs. So what if we can generate domestic hot water a completely different way? So on the left-hand side, you've got the product range, which is named Thermino. And that schematic shows a standard traditional unvented cylinder and a Sunamp battery. So you can see straight away there's quite a bit going on there with the pipe work, safety zone valves, expansion vessels. With the battery, all you need is a heat source and a cold pipe to it, and that is it. And because we can store 4 times more energy than water, it stands to reason it's going to be smaller. So this is a 300 litre cylinder, and this is the equivalent of the 300 litre cylinder. It will give you the same hot water. So again, in terms of social housing and some of the issues that social housing have, particularly with residents, is you've got to go there every year and do an annual safety check and potentially some maintenance, because any of the equipment associated with G3 building regulations fail, then you've got to fix it. We don't have those issues. Discharge pipe work, we don't need it. Happy to work with any either renewable source or heating source. You don't need an unvented certificate, so you don't need, as long as you're a competent plumber, that's all you need to be. It's fully recyclable. So everything within that unit is recyclable, from the phase change material, which becomes de-icer, to the metals, to the plastics within it. And there's no working parts in it. And because we have no water in there, the Legionella risk is negligible. So this is what it looks like. So this is a very sort of simple schematic, just showing you the heat exchanger. Inside it is like a twin pass heat exchanger. So you'll have a cold pipe coming in, which will run around one side of the heat exchanger, heat up, pick up the heat, and then it will run out the other side. So that battery there is running off electric grid. So you've got an embedded immersion heater, 3 kilowatt immersion heater within the phase change material. It's vacuum packed, so the heat loss is very, very low. And then we've got the material. So we'll pour the material in at the factory. It will be in liquid form. It will cool down, and then it's shipped out, ready to be installed. If you're using an air source heat pump or ground source or another heat source, you would have a 4-pipe system. So you've got these Tech-type fittings which are flexible, so you can swivel and turn it from the back, so you can bring your pipe work down that way, to the left, to the right of the unit. So the phase change material, one of the things we quite often get asked is it toxic? No, it's not. It's sodium acetate. Well, what's sodium acetate? Because that sounds aggressive. It's actually the stuff you put on salt and vinegar crisps. It's a flavouring and readily available in the food industry. So basically, once that's heated and it's at its liquid form, it will, if there's a problem or it leaks or someone drops it, it will come out and it will just be like brine water, essentially. So that's pretty much what the unit looks like. It's a very, very low tech piece of kit. It's just a heat exchanger. You've got a cold mains pipe coming to it, or a heating source coming to it, and then leaving it, and that is it. There's a little bit of electrics in there, depending what you're configuring it with. So in terms of its flexibility, so if you wanted to use photovoltaics, so if you wanted a PV system on the roof, or you've got an existing PV system on the roof, yes, we're happy with that. Just connect it into the immersion and trickle charge it. Once it's fully charged, then it'll toggle across and you can export it to the grid or around the building, wherever else you're going to use it. Grid electric, yeah, we're happy with that. Heat pump, yeah, air source heat pump, ground source heat pump, boiler, CHP, waste heat generator. We're looking at various projects where we're using waste heat at 65 degrees, district schemes, yeah. So anything within that range, you can use it with the heat battery. So if you wanted to use PV and then grid and then a boiler, you can do a combination of all of them. So it's really flexible for system design. We have a very, very simple user face. Now, most domestic hot water cylinders will not have LED batteries on them. You tend to put your hand on it and yeah, it's warm. But that'll be cool to touch because of the vacuum insulation we have. And there's no heat losses physically externally with that, because all we're doing is putting a cold pipe to it and whatever heat source. So in terms of the interface, power on, charging, half charged, you'll get this solid bar, and then fully charged, you'll get 2 solid bars. So as I've mentioned before, typical heat saving against the standard 300 litre, you're just under 2,000 kilowatt hours based on an annual typical energy usage. So what does that mean? Well, you're probably saving between 250, 300 quid a year just by taking out an old unvented cylinder and swapping it with a Sunamp battery. It'll be a little bit more with the energy rising costs come the 1st of April. So what have we looked at and what have we learned? So we've looked at the history of phase change materials, how they work, the difference between sensible heat and latent heat, its melting point at 58 degrees C. So we need 58 degrees temperature rise into the battery for the phase change material to melt and start absorbing latent heat. So ideal temperature range is between 60 and 75. We've looked at what if we can generate domestic hot water a completely different way on the road we're all on. So, who are we? Who is Sunamp? There's our mission statement. So I'll let you guys read that for a minute. I think all on that road. So Sunamp, we're based near Edinburgh. We're about 10 miles south of Edinburgh, founded by Andrew Bissell. So I've mentioned before, we work with the University of Edinburgh. But we're a fully UK business. Everything is manufactured, developed, and designed within the UK. So we support jobs within the local community. We give undergrad opportunities to degree-based engineers working in Edinburgh University. So we've got a really good standing relationship with the University of Edinburgh. All the technical training, stock, materials, the science team, everything's based in Scotland, in the UK. So in terms of where we are across the world now, we're active in 17 different countries. We just signed an agreement with China at COP26 in Glasgow. So we're now exporting phase change material in a £50 million deal with China. We've, under license, opened our second factory in South Korea, and we just opened offices in New York. So yeah, the North American market is opening for us. So, case studies. So this was the first major scale proof of concept design, and I'm happy to say it was based in the Northeast. Surrounding this project, there was a lot of negativity. It's not going to work, you can't do it, a lot of objections in all the meetings that went through, but collectively with the partners listed below, Gen 2, we took 7 tower blocks. So we had 364 apartments which had combination boilers in, so gas combis. One of the big issues that we're really concerned about was the fire risk. So, you know, we all know what happened at Grenfell in London. So they had high maintenance costs and there was a high fire risk. So the objectives were clear. We needed to do a full refurb. We wanted to take the gas boilers out. How are we going to do it? So what we did is we took a ground source bore, and then we took a thermal loop around the buildings, running it around about 9–10 degrees. And then what we did is we rose the temperature of the ground loop, the shared loop, through this little Kenta shoebox. So then that would run off to the heating side of it at around about 47–48 degrees. Needed to be independent metering for each resident, and the challenge was where we're going to put cylinders, where we're going to put hot water, because everybody talks around heat pumps. We tend to forget about the hot water side of things. So what we did is we had a challenge where we needed to fit batteries in the 400 mil wide cupboard, which was there. No discharge pipe work, no invented kits, and no Legionella risk. So essentially, Gen 2 wanted a fit and forget product which would generate hot water and would have low to zero maintenance, and that's what we did. The other issue we had was we didn't want to decant all the residents from the tower blocks, so we had to work around that as well. So what we did is we reduced the fire risk, took out all the gas, and your typical landlord savings, tenant savings, and reduced their CO2 emissions by 70%. So that proof of concept is now snowballed. We've got 2 tower blocks we're doing at the moment in Newcastle. We've got about 10 blocks we're just doing it in city Leeds, and in various cities around the country. London's the next big spot where we were doing quite a lot of the tower blocks, etc. So this is one of the early housing associations we were involved with. It's the East Heat project in Scotland. And we were just looking at a typical one-bed flat with a traditional hot water cylinder. So they had night storage units. Some of the issues they had was low water pressure and high heat losses. So we were looking to charge the batteries via the electric. So on a tariff like Economy 7 or Economy 10, leave the heating as it was. And typical consumption really exceeded double the average. So in terms of the heat loss, just by swapping, we went from 2.3 kilowatt hour day to 0.6 kilowatt hour day just by swapping out the tanks. So we were saving 1.6 kilowatts a day, so 600 kilowatt hours per annum, and the statistics to back that up. So we work with various air source heat pump manufacturers. This is just an indicative schematic of an installation. We are just doing some retrofits with Believe Housing in the northeast using this system. So we've got an air source heat pump in through a 3-port valve, which is diverting around doing its heating side. And then the controller, we'll bring the controller on during the small hours. So after midnight, it would charge the battery on a lower tariff, a low electrical tariff, charge the battery, and then you've got a full thermal store ready to go the next morning. Again, this is just a central or district scheme distribution pipework, either through a plate heat exchanger or a heat interface unit where you can meter it separately, and again running around the heating circuit, charging Sunamp. A little bit more on in terms of controls, etc., and off. So we're the only certified phase change material heat battery in the world, which was independently tested. So that was by Xavier Bain. 10,000 cycles equals about 13 years. We've independently tested it at Sunamp, and we switched it off after 50 years. So that's cycling twice a day, on the morning, on the night, changing phase, changing back, with about a 1% degradation in the material. So it's a really, really steady material. And it's a A+ rated product. We've got RAS approval, Kiwi approval, which are all the sort of accredited approvals you need for UK water regulations, and recently CCPD. Okay. So that's it, guys. I hope you got a little bit out